The Association of German Engineers and Hypothalamus Artificial Intelligence. Present the conference. Parallel and Distributed Analytics, Applied to Transport and Logistics Chains. Conference prepared and edited by Jesus Velasquez Bermudez, who has won the following awards. Research in Logistic, 2006, awarded by the Colombian Association of Logistics, ACOLOG. Innovation and Logistic Excellence, 2006, awarded by GS1 Colombia and Logística, GS1 Global Network. Parallel and Distributed Analytics Applied to Transport and Logistics Chains. The economic value added by advanced mathematical models. It is represented by operations research, billions and billions of dollars in social and economic benefits. Analytics is one of the pillars of the so-called smart computing. This is based on the statement of Andrew Bartels of Forrester Research, who in the study Smart Computing drives the new era of IT growth states, verbatim. Smart computing is a new generation of integrated hardware, software, and network technologies that provide IT systems, with real-time awareness of the real world and advanced analytics, to help people make more intelligent decisions about alternatives and actions that will optimize business processes and business balance sheet results. For more than 4 decades, winners of the Edelman Award have been recognized for transforming how they approach some of the world's most complex problems. The 2020 finalists are no exception, with revolutionary contributions in robotics, cruise industry pricing and booking, railway planning and productivity, IT system sustainability, corporate decision-making, and retail inventory operations. Finalists for the Edelman Award have contributed to a cumulative impact of more than $292 billion since the award's inception. 2020 Franz Edelman Award was won by Intel. The tech giant receives coveted award for integrating product architecture design with supply chain planning. Below are the success stories reported by the finalists of Edelman 2020. Intel has earned $25 billion by applying advanced analytics. Intel face efficient product feature design coupled with supply chain planning. It is critical to Intel's success given its scale, complexity of its products and manufacturing processes, and the highly capital-intensive nature of the semiconductor business. In response to an exponential increase in complexities, Intel developed an innovative set of capabilities, using advanced analytics, that span product feature design through supply chain planning, with the goal of maximizing revenue while minimizing cost. This set of capabilities is fast and effective, enabling analysis of many more business scenarios, in much less time than previous solutions, while providing superior results including faster response to customers. Implementation of this capability over the majority of Intel's product portfolio has provided average annual benefits in increased revenue and decreased cost of $1.9 billion and $1.5 billion, respectively, with a total benefit of $21.2 billion to date, while also contributing to Intel's environmental goals of reducing water usage and preventing wastewater. Deutsche Bahn, the largest European railway company, is moving more efficiently thanks, in part to a new decision support system. The system optimizes train rotations in cargo, regional and long-distance passenger transport divisions. The changes have resulted in direct savings in addition to better planning and productivity. The productivity of the locomotives and railcars has increased up to 10%, while the time savings were up to 80%. In the middle of the first decade of this century, Thomas Davenport and Jean Harries published the book Competing on Analytics. In this book, analytics is classified into 3 types. Descriptive focuses on asking questions to databases, using filters, in order to know the conditions in which certain events occur. Predictive, oriented to project what may happen in the future, and prescriptive, oriented to the optimization of decisions, generally based on the results obtained in predictive analytics. In the diagram prepared by IBM, at the beginning of the past decade, you can visualize. Optimization is the methodology that provides the most competitive advantage and ability in highly complex mathematical modeling. This means that optimization is the way to capitalize all the effort made with predictive analytics models, and descriptive analytics does not generate value, like mathematical modeling. Jeremy Shapiro, professor of the Massachusetts Institute of Technology, says, The primary benefit of a DSS is the explicit reduction in costs and the increase in profits. Cost reduction of 8% performed by our client is not atypical. In our experience, the integrated analysis of planning problems, using mathematical models, determines strategies between 3 and 20% cheaper. Many companies do not allow them to publish their positive experiences, as they consider that an advanced decision support system gives them a competitive advantage. Sparse analytics or parallel and distributed analytics. There are two approaches to process data from a super measurement system that provides a non-enumerating amount of data, in real time and asynchronously: parallel analytics and distributed analytics. These two terms seem to be the same, but they are different and complementary terms. The parallelism and distribution of computing processing goes beyond the simple construction of parallel mathematical algorithms. It implies a way of facing problems with the bottom-up approach, from the description of atoms to integrating the vision of the entire system. It is a way of thinking about mathematics, according to the development of computer technologies. This is consistent with the abolition of monolithic computer applications, to make way for distributed applications based on microservices. Then the next step of advanced analytics is sparse analytics, which is based on parallel and distributed analytics. Asynchronous parallel analytics, called asynchronous parallel optimization by Velasquez, in 1995, 1997, and 1998, is defined as the act of solving a mathematical problem, using multiple cores on a computer, or on a computer grid, using modern multiprocessing environments, uniting the theories of decomposition and partition of large systems, that allow to structure complex multi-level mathematical models. Parallel analytics distributes workloads for data analysis across multiple nodes in a server cluster, rather than addressing a large problem on a single supernode. The algorithms run on each node, processing a subset of the data. When processing is complete, or whenever required, datasets are aggregated, or rejoined, to generate collective information. There are many advantages of the asynchronous parallel approach. Less time to get information. By putting multiple nodes to work on the same problem, you can get insights from the data much more quickly than would be possible by running an analytics application on a single supernode with linear processing. This is a huge benefit when you want to get quick responses from massive amounts of data, and asynchronous processing allows to produce information that can be stored in memory until it is required by some subproblem. This speeds up the solution. In addition, it requires less demand for resources, avoiding congestion in computer systems. Distributed analytics is based on parallel analytics, and it is the distribution of the mathematical modeling process in many agents that act simultaneous and independently when they received information from its exogenous environment. The process can be summarized in the following steps. From a top-down process analysis, is possible to construct mathematical or logical rules of interaction between multiple agents, representing each one a part of the system. Jointly, all the agents can represent the state of the reality. Starting from math, or logic rules, following an approach bottom-up, is possible to build segmented, or atomized, models of the real world. Using asynchronous parallel processing, it is possible to define the simultaneous actions of all agents that keep on the right path a cyber-physical system. This processing is different from the traditional one, based on the synchronized use of mathematical models that are executed periodically. Autonomous real-time distributed optimization. Mathematically, this process may be supported by large-scale optimization algorithms, aimed at solving very large optimization mathematical problems, based on the intensive use of methodologies for partitioning and decomposition of systems. New technologies and big data shift from traditional optimization based on synchronized moments, to modern optimization, based on real-time events, in which models will run autonomously, when necessary, by events. Autonomous real-time distributed analytics is a topic open to researchers in advanced analytics. Artificial brains is a disruptive modeling methodologies for Industry 4.0, based on the integration of artificial intelligence and mathematical programming. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The decision support systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that controls the workflow of the models of the decision support system. It includes a general math language between algorithms that guarantees that the system is in the optimal path. This is based on the duality theory. In real-time and uncertain systems, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. The algorithm that simulates the hypothalamus is assembled by Optex, the HAI's artificial intelligence, to generate mathematical programming solutions, using the models that traditionally make up a decision support system. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. Autonomous real-time routing and distributed optimization. Industry 4.0 real-time routing. Challenge: modify the traditional vehicle routing process to access to the Industry 4.0 environment. Solution: it implies that all agents, the dispatcher and the vehicles, need to know what information they need to take from smart metering systems, and what information they need to provide to other agents to they make their decisions, to keep the system end-to-end on the path to optimality. This is possible using asynchronous parallel optimization methodologies. In the case of freight transport, the traditional process of planning logistics operations in a city could be carried out as follows. At the end of a period, for example, a day, or a shift, a dispatcher plans all routes to fulfill the deliveries, or pickups of the next period. This may involve solving the problem of routing vehicles with time windows on customers, optimizing an objective function according to the company's business rules. Even for small fleets of vehicles, this is a complex mathematical problem, when we consider all the limitations in real systems. The dispatcher generates the route, the sequence of clients, and possibly the route, the sequence of streets, for each vehicle that will be used that period. This schedule is fixed, and it may be considering static travel times for the entire period. That is not true. At the end of the period, the dispatcher updates the database considering the contingencies that occurred during the period, and will start the process again. Given the reality of the process, in which travel times are uncertain, and change dynamically during the period, the programming carried out cannot be optimal. To transit the path of optimality, a dynamic scheduling can use all the power offered by smart metering systems, like Waze, which, in any time, provides rich information for each truck. The best path, or a route close to the best, and a good forecast of the actual travel time. Additionally, it may be possible to obtain historical data on travel times, differentiated by time of day, day of the week of the month, etc. This allows the dispatcher to have up-to-date information to solve a vehicle route issue with time-dependent time and travel time windows, which should produce better results. The dispatch process can be adjusted as follows. At a certain point in the period, the dispatcher plans all routes solving the routing problem with time windows and time-dependent travel time, taking as input data the latest database updated by all smart metering systems, that is, the trucks, Waze, hydroclimatological, and traffic databases. This process would be carried out centrally, to generate a forecast of the route of each vehicle, to be used that day. Each route must be uploaded to MSD, a mobile smart device, such as a Raspberry computer, VDO, iPhone, or iPad, through which data is received from a SM, a smart metering system, such as Waze. During the route, at the end of service on a client, the MSD mobile device asks SM for information about the estimated travel times and optimal routes to complete the route. With the new information, the MSD can solve a TSP, travel salesman problem, to recalculate the optimal missing route, that is customer service order, and attention times. MSD send that information to the dispatcher, so that, if necessary, it will rearrange the planning of all routes. The approach may be conceived as an artificial brain composed of a network of mathematical models, the VRP dispatcher, TSP problems in trucks, and the mathematical models provided by Waze, and the existing measurement systems. The communication between the algorithms of mathematical problems must be asynchronous, since events occur in the system. Two levels of interconnection can be visualized, with the dispatcher, to coordinate the entire system, and between trucks, to improve truck decisions. To establish the communication protocol between agents, the decoupled view of a routing problem can be considered, which may be solved using Bender's theory, Lagrangian relaxation, column generation, or cross-decomposition. These methodologies already include math communication between algorithms, to improve the solution of the integral optimization problem. Autonomous real-time energy optimization. Fuel consumption can account for up to 63.9% of the variable operating costs of a heavy ground transport fleet, therefore, it is a critical factor in the planning and scheduling of truck routes. In state-of-the-art cargo transport vehicles, the engines are electronic, digitally controlled, with telemetry capability of the nearby environment that optimizes fuel efficiency. This autonomous capability of modern vehicles can be called optimal short-range control. There is another level of operations planning of a fleet of vehicles that is long-range, and that must contemplate the full route of the vehicle, and the planned times of arrival. The importance of this planning is seen in the performance curve of an engine in which operating in a range of 1,100 to 2,000 revolutions per minute results in optimal performance between 1,500 and 1,800 RPM, according to the truck's provider. However, optimal power performance, with lower fuel consumption, is below 1,500 revolutions per minute. As in any vehicle, the compromise between speed and economy do not move in the same direction. The graph presents the differences in performance of the engines of 5 types of truck. So, optimizing energy consumption is complex because the consumption function is not linear and depends on factors that are the result of decision-making, such as vehicle charging and geoposition. Route-dependent factors, which can be divided into static, for example, slope, roughness, and dynamic, for example, traffic, route weather. While the mathematical problem is complex, the power of parallel computing, the effectiveness of optimization algorithms, and online databases, make it possible to solve it in the Industry 4.0 environment. This problem can be solved on MSD computers in vehicles. Autonomous real-time distributed traffic optimization. Challenge: using the Industry 4.0 environment to optimize the flow of vehicles in a large region. Solution: implement a mathematical model based on the concepts of autonomous real-time distributed optimization. Optimizing traffic light sync in a traffic system is a complex problem, primarily in complex areas with complex traffic networks. Solving the integrated problem may be impossible. Splitting the problem by zones may make easy to solve the total problem. However, the dynamic nature of the problem, and its spatial dispersion, make attempting an optimal solution utopian. The connectivity between the different problems, based on principles of large-scale mathematical optimization, ensure that the system travels the path of optimality, close to the optimal solution. Today's information capture-intensive systems, smart metering, allow optimal operating conditions to change the decisions dynamically, as traffic behavior changes in the city. From the traditional planner's point of view, the region can be seen as a single zone, which he, or she, want to optimize the traffic network, through a monolithic multi-period advanced analytical model. For a small town, it is possible that today's computers can solve the monolithic model, but for a big city it is impossible. It is possible to attempt to solve the monolithic problem using large-scale optimization methodologies, based on the partitioning and decomposition of the mathematical problem. To do this, the entire region can be divided into zones, each of them associating a multi-period subproblem. In turn, these subproblems can be divided into as many subproblems as periods, to achieve the highest level of atomization. Each zone may have its own control center, which may be a computer that collects signals from the zone, and solves the problem for that zone. This approach could increase the size of the region, but in the speaker's opinion, it will still be insufficient for large regions. The Cell Transmission Model, CTM. CTM is a popular numerical method proposed by Carlos de Ganzo, in 1994, to solve the kinematic wave equation for traffic problems. CTM predicts macroscopic traffic behavior on a given corridor, by evaluating the flow and density, at finite number of intermediate points, at different time steps. This is done by dividing the corridor into homogeneous cells starting downstream. The length of the cell is chosen such that it is approximately equal to the distance traveled by free-flow traffic in one evaluation time step. The Lighthill-Witham-Richards, LWR, is a model commonly used for traffic flow based on CTM. There are three fundamental variables: flow Q, the rate at which vehicles pass a point; density K, the spatial concentration of vehicles; and speed U, the average rate of travel. The Newell-de Ganzo, ND, method is an easier alternative to solving the LWR model. ND assume a triangular fundamental diagram with only two wave speeds, UF, for the uncongested portion, and -W, for the congested portion. In a triangular curve, speed does not drop, until density exceeds the critical density and congestion begin. The density will grow until finally the traffic stops. The graph presents a sample to calibrate the parameters of the LWR model. Traffic network optimization modeling. Some traffic mathematical modeling applications are: dynamic traffic assignment, network design problem, traffic operations, emergency evacuation, and hybrid simulation. Modeling is carried out at the intersection level, with or without traffic lights. At each intersection, the flow of streets arriving or leaving must be modeled. The diagram presents the modeling in a round point. Network-level coordinated speed optimization and traffic light control. The modeling presented below is based, mainly, in the paper Optimal Network-Level Traffic Signal Control, a Bender's decomposition-based solution algorithm, published in 2019. The network-level traffic signal timing optimization problem is a mixed integer nonlinear program based on the cell transmission model that captures the fundamental flow density diagram of the CTM explicitly, by considering closed-form constraints, and thus, eliminates the flow holding back problem. The proposed solution algorithm is based on the Bender's decomposition technique. It decomposes the original MIM to an equivalent integer program, the master problem, and a MIM subproblems. A distributed optimization and coordination algorithm that can handle the computational complexity of the problem and find near-optimal solutions in real time. The figure shows the conceptual representation of the proposed methodology. The distributed optimization decomposes the network-level problem into several standalone intersection-level subproblems and solves them in parallel. The decomposition is achieved by identifying the constraints that represent interrelationships between subproblems and relaxing them. Distributed coordination pushes solutions towards global optimality by exchanging information among subproblems that share a relaxed constraint and reinforcing the relaxed constraints in subproblems by incorporating the information that is received from other subproblems in them. Then distributed optimization decomposes the network-level coordinated signal timing and speed optimization problem into several standalone intersection-level subproblems. A signal controller will be responsible for finding the optimal signal timing and the average speed of approaching vehicles. This decomposition is equivalent to cutting the links that connect intersections. In other words, The constraints that connect two neighboring intersections are relaxed, and each intersection is optimized as a standalone subsystem. To explain the process, let define V as the set of all intersection nodes in a network. Figure shows a decomposed network containing intersections N and M, belonging to V. The two intersections are decomposed by breaking the shared links between them. Intersection N is converted to a standalone subnetwork by adding dummy source cells CNO and dummy sink cells CNS to the boundaries of the intersection. The flow YN belongs to the broken links that enter intersection N from neighboring intersections. This method is incorporated in model predictive control to account the dynamic nature of the problem and further reduce the computational complexity. For those interested in the subject, the paper Network-Level Coordinated Optimization and Traffic Light Control for Connected and Automated Vehicles, published in 2021, presents the complete formulation of the problem in reference. The image shows the summary of the objective function. Finally, the diagram presents the proposed two-level structure using Bender's decomposition. Perhaps the solution time may be speed up if more levels are introduced in the hierarchical structure. In this case, it is proposed to include a level associated with the main traffic corridors that interconnect the region. It is possible to extend the proposed model using the concepts of autonomous real-time optimization. The approach may be conceived as an artificial brain composed of a network of mathematical models, general coordinator, the master problem traffic corridor coordinators intersection subproblems. The communication between the algorithms of mathematical problems must be asynchronous, operating continuously. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972, in the book Human Problem Solving wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.